Before, we looked at the situation for an ideal lens. We will now look at what happens if the lens behaves non-ideally. And typically, all lenses will have a little bit of non-ideal behavior. For instance, if we look at rays going through the thinner part of the lens, or at an area where the lens surface is more curved, leading to a higher deflection of the beam. So first, we consider the lower line here, which represents a ray of light traveling very close paraxially to the axis. So this ray nicely goes through the focus of the beam here. And we have seen previously that we can indicate a deflection angle delta alpha for the ray as a function of the lens action. Now if we have a ray traveling higher up to the lens, we will hit a stronger curved area of the lens, leading to a stronger deflection of the beam. So this ray will travel across the optical axis at a point closer to the lens with respect to the focal point than the paraxial ray does. So also in this case, we have an angular deflection here, which now of course is larger than the angular deflection that I have indicated here. Note that the upper ray traveling here, crossing the optical axis at a previous point and crossing the focal plane at a different position than the paraxial ray does, gives rise to a blurring of a focus that we would have here, which is of course important if we want to consider imaging at the highest possible resolution, because then we want to have an as tight as possible focal point here. So in the previous movie, I've introduced the opening angle of the beam, which we can indicate again here as alpha image, which in the remainder I will just abbreviate as alpha, as we don't look at the angle on the object side. Now also the blur here is characterized by a typical radius, which is indicated here, and which I will denote by R spherical, where spherical stands for spherical aberrations. Spherical aberrations are typically the aberrations induced by the lens as a result of its non-ideal operation. Now let's first look at what a lens ideally should do. So the lens should deflect rays coming in parallel to the axis with a deflection angle delta alpha. And this deflection angle should be the same, irrespective of where the ray comes in into the lens plane. But we can see that if a ray hits the lens at a distance minus h object, the sign of the angular deviation should be opposite. So we see that we can write that delta alpha minus h should be equal to delta alpha. In addition to the equation here, we can see that the action of the lens should also be such that a ray hitting the lens plane further away from the optical axis should be deflected more, so that both rays travel through the same focal distance. Ideally, this behavior should be linear, so delta alpha should be equal to a constant factor times the height at which the ray hits the lens plane. We know that for the ideal lens, indicated by the ray here, that this delta alpha angle, the tangent should be equal to h over f, which in the small angle approximation is equivalent to delta alpha is h over f. This is for an ideal lens. We can see that if we moved further from the axis, and this equation would still hold, also this ray would go through the axis here with a new h and the same f. Now what about the non-ideal behavior that we have here? So we're going to write that down here. So we have a non-ideal lens. And for the non-ideal lens, the equation that we have here or here does not hold. In general, we see that the deflection becomes stronger. So we can write this as a factor a1 times h, so the ideal lens behavior, plus additional factors. Now we should bear in mind that also the lens should be spherically symmetric, so this equation should hold. So we can write the delta alpha here in a power expansion, but in this case we should omit all the even powers, because they would give a wrong factor here. So we can write this now as a factor a3 times h to the power 3, a5 h to the power 5, and subsequently smaller factors added to this equation. Now for the remainder of this, now for the purpose of this derivation here, I will omit all the higher terms that we have here and focus on the first term in the aberration expansion. So let's look at the graph we have here. So we see that for the aberrated ray, delta alpha is given by the angle here, which does not include h anymore, but includes an additional factor, r spherical. So we see that delta alpha equals h plus r spherical over the focal distance f that we have here. So if we write this down further, we can see that this is a factor h over f plus a factor r spherical over f, where the first term that we have here is our ideal lens equation. So this is the same as the coefficient a1 that we have here. So we see that this is equal to our factor a1 times h plus r spherical over f, where we now have that a1 equals 1 over f, and the first coefficient in our expansion here. Now we also see that the second term, a3 h to the power 3, should be equivalent to r spherical over f. So from this we can see that r spherical is equal to our factor a3 times h to the power 3 times the focal distance f. We can also write this in an expression including the opening angle of the beam. So we see here that the opening angle of the beam alpha is given by h over f. So if we use alpha is h over f, so the ideal situation for the opening angle. So if we take these two together, we see that the radius of the spherical aberration, r spherical, is equal to a3 times the focal distance to the power 4 times the opening angle of the ideal beam cubed. So now we see that the radius of spherical aberration, so the blur in the focus that we have, depends as a power 3 on the opening angle of the ideal beam. So the larger the opening angle, the spherical aberration will increase with a factor cubed. So this is actually one of the reasons why in electron microscopy system we always have a very small opening angle, as we'll see in later lectures. Now we also have a term here, a3 times the focal distance to the power 4, which is a property of the lens, which we denote as the spherical aberration coefficient. So a3 is a property of the lens, and we see that a stronger focusing lens has higher spherical aberration, corresponding to the fact that we see in the optical case a stronger focusing lens has a higher curvature, leading to more deviation from the deflection for more off-axis rays. Now in this case we denote the spherical aberration coefficient as the spherical aberration coefficient of an infinity system. And note that our derivation here was for a parallel incoming beam, where all the rays should go through the focal point here, which is what we typically denote as an infinity system. It's the inverse of a system where we have a source in the focal plane leading to a parallel exiting lens, so a lens with a focus at infinity. Now in a practical situation, we of course not always have a situation with an infinity system. We may have a system with a finite magnification, an object on the object side of the plane and an image on the image side of the plane. In this case, the angular deflection that we will have here and the deviation from the angular deflection will be larger because it also includes an angle on the object side of the plane. So in this case, we will work with the spherical aberration coefficient for a specific magnification, And it can be derived that this is dependent on the infinity system as 1 plus the transverse magnification of the system to the power 4 times the infinity spherical aberration coefficient. And we will look in a bit more detail at this equation in the assignment that you will have to do after the first 2 lectures.